Okay, so now I'd like to take a look at filters, image filters in processing. The first ones to mention are, there's a bunch of built-in image filters that you can look at in processing. So you could take a look at the filter method that provides you with a lot of, filters that you would commonly find in programs like Photoshop and other image editing programs that let you, do things like threshold and posterize and blur and so on. So let's have a quick look at filter demo. So as in previous examples, we're using our nice church photo for this one. And you can see here that we have a little sketch that loads in the image. Let me just arrange things here a bit. We have a sketch loads in our image and sets the size of the screen so we can fit it in, and then we simply call the filter method, which is a method of the image here, and by passing in one of these values like posterize, gray, threshold, invert, we can apply different filters. So as you can see there, so far in this example we're applying the blur filter. If you look in the documentation, you'll see what each filter has different kinds of parameters that affect it. So you check out the documentation for that. If we run this now, we'll see what the blur filter does with that particular setting. We can also try posterize, is always nice. There's a posterize filter. Or a grey filter, which changes the image to a grayscale. We can do combinations, of course, so if we want to apply posterize and the grey filter and invert, we can do that, and we get that effect there, and we can mush all that up with the blur filter. So you get the idea. It's just like playing with Photoshop. You can use these built-in filters to achieve a wide range of effects. They're quite powerful, and you don't need to know very much about what's going on in those filter methods in order to use them. However, it's useful as interactive media developers to have some idea of how these filters work and how, if you need to, you could start to create your own filters. So if we look at more sophisticated filters, we might we'll look at something like these spatial filters here. So what we have here is our input image on the left, our output image on the right, and we have this a matrix of numbers which is called the kernel, spelt with a K. And the way we calculate what the value of how the value of an input pixel is transformed into an output pixel, oh goodness me, we do some matrix maths in order to convert the value of an input pixel to the value of the output pixel. So if we have this pixel here, which is E, and we apply some kernel to it with a bunch of numbers W1, W2, W3, etc. The way we calculate the value of the output pixel E dashed is it's the value of the first number in the kernel matrix multiplied by the value of the pixel up here, pixel A, which is one of E's neighbors, plus the value of W2 times pixel B, which is the pixel immediately above our pixel E, plus W3 times C, plus W4 times D, plus W5 times E. So we include the value of the original pixel as well as its neighbors. So you get the idea that we're applying the value of each of these numbers in the kernel and multiplying it by the pixels which surround our original pixel, and we add those all together to produce the final value of the output pixel. This is how spatial filters work. A particular kind of spatial filter is a convolution filter, and this is basically where an averaging function is applied to a set of pixels in the source image, which is kind of what we were just talking about. So the set of weights applied is known as the kernel, as I mentioned. So if you think about it, if we use a kernel which has all zeros except for the middle value, when we multiply a pixel, when we calculate the output value for a given pixel, it's always going to output the value of that pixel, and it will output 0 times the value of that pixel's neighbors. So in other words, applying the identity kernel is going to transform a source image into an identical copy image. So all the pixels will be not transformed at all, they will be exactly the same as they originally were. If we apply a kernel like this one, we are saying that the value of an output pixel is 1/9 of the value, it is made up of 1/9 of the value of all of its neighboring pixels and itself. So in other words, we're kind of getting the average value of the 9 pixels that make up the source pixel and its neighbors. So if you think about it a little bit, that should give us a kind of blurring effect, that all the pixels colors will tend to sort of be moved closer together, and sharp differences between pixels will be reduced. Let me there's some other example kernel matrices here, which we'll apply in a sec. Creating these matrices yourself is probably largely a matter of trial and error, really, but you'll also find, if you Google on the web, you'll find a bunch of different matrices that have different effects. We're talking here about 3x3 matrices, but there are certain effects that will have bigger dimensions, 5x5 matrices and things like that, and larger. But you can see, for example, a matrix like this. Again, it's a little bit hard to visualize, but if you think about what effect this would have, a matrix like this would have on pixels, where one pixel is very different in color to its neighboring pixels, you'll see that it sort of highlights, it will tend to increase the brightness of pixels which are different to their neighbors, and when pixels aren't different to their neighbors, it will tend to make things it will tend to leave them more or less as they are. But let's mess around with some of these filters. I think the easiest way to see what they do really is to run some code which applies them. I'm not going to talk through the code in this case because it does get a little bit complicated and the details are not that important for this class. You can always check out the code yourself and figure out what's going on if you wish. But really what the code is doing is applying a bunch of these different matrices and using them to transform the source image, which is our church again, and apply these filters to that church. So if we run the code, and to show you this one of the simplest examples, if we run the code and we look at, on the left here is our source image, and on the right is the image after the convolution filter has been applied. This is the mean kernel. So this is the one which basically sets a pixel value to be the average of that pixel's value and all its neighbors. And if you look carefully at the difference between the image on the left and the right, you'll sort of see the effect that has. It kind of smooths everything out, makes everything slightly blurry. So So that's the effect of a mean kernel, an averaging kernel. The sharpened kernel that I talked about before is this one. So you can see there that's bringing out where there are regions of sort of contrast. It's bringing those out more and emphasizing those. Edge detection is quite an interesting one. Again, it's bringing out where pixels tend to be different to their neighbors. It's really emphasizing that. I forget what number. Edge detection looks something like that. So showing us where the edges are in an image. And if you look carefully at these matrices, you can start to kind of nut out, okay, well, what happens if I'm applying this kernel and it's applying it to a region where we have a lot of black pixels surrounding a very bright white pixel? What is the output going to be? What happens if it's all black? What happens if it's in between? You'll start to understand how these filters work and maybe start to mess around with your own numbers and see what results you get. Some other interesting examples are a kernel like this one gives you this emboss effect, like this, like you've kind of, it's kind of like almost a 3D effect, like this image has been stamped into some soft tin foil or some metal or something like that. So if you Google around, you'll see there's a heap of different convolution filters, and all I've done here is sort of highlight the basic concept of how they work, and hopefully from looking at just some of these example convolution filters, you'll see that it's really a very powerful technique. So that's it for filters. In this subject, it's not important to understand in great depth the maths that's going on or anything like that. It's more important to understand what filters can do and get some sense of how they work and how you can mess around with them and engage with them and use them to create effective user experiences. Okay, that's it for filters. Next up, we'll be talking about introduction to 3D graphics and processing.